Okay, so I apologize. I just was saying that I apologize for being a little late today. Yeah, I'm muted. So hopefully, oh wait, still muted. Oh, okay. All right. On my screen, I see it's still muted, but it looks like it's okay. All right. Okay, lecture notes, if you want to grab them, are on the handouts and lectures. Lecture 14, AC Power. So we're going to start with chapter 8 in the book. So if you guys want to start reading that and becoming familiar with that material, we're going to cover AC power from that. We're going to do a little bit of review from chapter 7, which was about phasers. And then we're going to go to chapter 13 also. So this section will be chapter 8, a review, or some of you may need to relearn the material in chapter 7 and then chapter 13. So we'll start with chapter 8. So the first goal of today is to understand what the average and RMS values mean for periodic waveforms. This is our first goal that we're going to talk about. So when we look at a system like this, we have kind of a source that can be put into a Thevenin equivalent with a resistor and a voltage source, and then we usually have some type of a load. And in the past, we've usually talked about a load being more of just a resistive load, like a speaker itself would be a resistive load. But a lot of times you'll have either an inductance or a capacitance, depending on the load. If you have a chip itself, there's capacitance between the chip pins and the circuit itself. So that would be a parasitic, meaning that it's not something that's physical, but is actually creating a capacitor between the plate of the pin itself and then the wire that you are connecting it to. So there are what's called parasitics in circuits. So most things have either capacitor or inductance to them. So they're going to be a complex load. So that's what we're going to start talking about. And then the other thing we want to do a lot of times is be able to create enough power going to those elements. If it's a speaker, you want to be able to have enough power to drive that speaker. If it's some other load, you want to match that network so that it will get the maximum power it can get into that system. So that's what we're going to kind of go backwards to understand some terminology, and then we're going to move forward to figure out, how do I figure out what that max power would be as far as those components that need to be in this matching network. Does that make sense, what we're going to try to achieve? Okay. So first step is to understand some terminology. And so with the terminology, sorry. We want to understand what instantaneous means. So instantaneous is what we've been referring to with what we found so far when we find something such as I of t or V of t. So I of t and V of t, that equation is what we consider an instantaneous value. Okay, so when I refer to instantaneous, that's what it means by instantaneous. It's just referring back to what we've done previous, where we've discovered or derived and understood that V of t or I of t or other component within the circuit. The other term is now average. So what does average mean? From math, average means that you're taking the integral of your function that you're trying to find the average over. And what does the integral give you? Correct. So it's giving you the area under the curve. So sometimes our curves that we're going to find the average are going to be a sinusoid. So when you have a sinusoid and you think about one period of a sinusoid, what would be the average on a sinusoidal period? Let me draw this. So if I was to take this and I wanted to find the average, and it's a sinusoid, what's the average of this if I'm finding the area under this curve? It'll be 0, right? Because this is going to equal the negative of that. So our average here would be considered 0. So sometimes our functions that we're finding, though, are not going to be nice sinusoids. And so if it's a triangle, you're going to find the area is going to be easier than taking the full integral. Or if it's a piecewise linear where you have the U of t functions, then you have a square, which is easier to find the area of a square. So sometimes you will want to take the integral. Sometimes you'll be able to look at it and say, well, I can figure out the area geometrically. So either way, we would find the average, and then you're going to take it over the time period of whatever that function is, and that gives you the average. So this is a definition of average. So that is something you have to understand. So we're going to go back to this equation. So either memorize it or have it handy. The next term that we're going to talk about is called the root mean square, or RMS value. So the RMS value, when you're talking about mean, the mean means the same thing as average. Yeah, sorry. Love that this, there we go. There we go. I can type probably faster than I can write it. So the mean usually equals the average. So if we're talking about the root mean square, then average of the mean is going to be that function. So you have 0 to t of whatever I'm finding the average over dt. And then the mean of that, or this is the mean. And then when we talk about the root, that means the square root. So we're going to square root this. And the square portion is going to be the function that's squared. So this is how you remember this formula. To be able to get the root mean square. And how do you interpret, or what does this mean to find the root mean square? So the root mean square is, now we have, when we're talking about complex, if we have, I think this is an easy way to kind of understand what this means, is that we want the root mean square to give us the same power as when we are in the DC. So if I look at this, how much power is going to this 5 ohms? Remember, power is what? Voltage times the current. And you can write I as far as V over R. And so in this case, you have V squared over R. And so, wait, VIR, yeah, that is right. So what would this be here? So 20, is that right? 20 watts. Okay, so in DC, if we have 10 volts DC, we want 20 watts. So we want the same thing here, is that we want to use this RMS value that is now for a periodic voltage. We want that to equal the same thing and still give us 20 watts. So that's what the RMS value does, is it takes the AC signal and makes it seem as if it's effective, the same effectiveness as what the power given to us in DC. Does that make sense? So that's kind of what the goal of the RMS does. And so to get there, we would use that equation that I just went through. So that's the idea of why we're doing the RMS value. And then the mathematical portion of it is the equation itself. So this will be another equation that you need to know. So let's now look at kind of some examples of these. So if I'm given this signal and it's in current, I want to determine the average of this signal and the RMS values of this periodic current waveform.
I can't follow you here on your server.
Sure I did. To refresh. Is anybody else having trouble getting the notes? Anybody grab the notes? You guys have them? I am not sure why.
Yeah, just to inform you.
Are you on the internet?
Yeah, I am.
I would close this out.
Yeah. You want more?
Can you close it fully? I don't know how to.
Yeah.
Then reopen it.
Yeah, open it again.
Uh-huh.
Yeah. Like that. You want to restart or maybe? Right now?
Yeah, maybe restart it.
Okay.
I don't know. The others are able to get it,
Thank
so.
you.
Uh-huh. All right, so how are we going to find? This is annoying without this pencil. So we're going to use this function to find the average. All right, so we need to write this function to be able to find the average of that. So how do we write this equation? So from 0 to 4, it's going to just be a flat minus 12, right? So this function, we would write I of t equals minus 12 for t between 0 and 4. How do we write that portion of it right here? Just remember how to write the. Okay, mx plus b is the line equation. So how do we find the slope? Yep, so rise over run. That's how I remember that one. So rise in this case is going to be negative 12 over, the run was going to be over 4. Wait, sorry, rise is going to be still 12. So 3 is going to be our M. And then how do you know where it connects here for B? B is the intercept at the slope. Intercept at the Y. Oh my goodness. The y-intercept. There we go. So if the slope is 3 between 8 and 4, you're going to go 3 more. Wait, you're going to go. It would be minus 12 again, right? Between over 4, a time period of 4, you go down by minus 12. And so another 4 is going to be minus 12. So this would be minus 24. So this is going to be 3x minus, or 3t, sorry, 3t minus 24 between 4 and 8. Not do well. And then this one is going to be, again, you have a same slope, but the intercept again is going to be 4 more. So it's going to be 1236. And so this one will be 3t minus 36 for between 8 and 12. And then you have again another 4 time period between 12 and 16, where it's just a minus 12 again. Are you guys following how to write this? Okay, so now from here, we are going to use the integration. So 1 over t. And so the time period for the first one is 0 to 4. And then the time period is 16 fully. So our I average is going to equal 1/16. And then integrate each of these intervals. So 0 to 4 minus 12 dt. And then plus 4 to 8, 3t minus 24 dt. Plus 8 to 12, 3t minus 36 dt. And then plus 12 to 16 minus 12 dt again. So integrating minus 12 is just going to be 4 minus 0. So 12 minus 12t, 4 minus 0. So and then t minus 12t, so 4 minus 0 will be what you'll plug in for that one. And then 3t minus 24 let's see, 3t squared over 2 minus 24t. And then evaluate it from 8 and then plug in 8 and then plug in 4. And then again, evaluate it at 12. And then at 8. And then minus 12, 16 minus 12. Okay, and then that ends up being minus 9x. So the first one you can see is just going to be the area, minus 12 times 4, which is the area underneath that rectangle. And then the other two will give you like a half of the base times the height, if you want to do it that way. So you can just do it with geometry instead if you don't want to do the integration. Does that make sense? Yes. So the time period is where it is going to be repeating. And so you can see at the beginning, this is only 0 to 4 seconds. And so when you look at the repeat, it would be the beginning portion would be 4 seconds and then the triangle portions. So that's only going to be this portion here. And so you need to add on that portion at the end to make it periodic. Because the periodicity is not from 12 to 24, which would be, yeah, 6 or no, or 8 is not 8 instead. Does that make, do you see that now? Okay, so his question was, how come it's 1/16? So that time period T is your period of how often it's repeating. And so in this case, it's 0 to 16. So that's why it's 1/16 there. All right, other questions?
So, sorry, the average is negative, not negative 18.
Yeah, the average is -9.
So it's only over one
period.
one period.
Yep, you do it just over one period, even though this is drawn as 2 periods in there. It's only, you find the average over just one time period. That's why you're taking 1/T also. So even though this graph, could go on And so you just find the average over one time period. Yes. Any other questions? Second. Okay, so the other question online was why the second integral is evaluated at 8. So our, what do you call these numbers? Just the range that we're evaluating it over from 4 to 8 in the second one. And remember, you take the top one and then you subtract off the bottom one. And so that's why this one's at 8 and this one's at 4. Yes, integration bounds. Thank you, Timber. Okay. Alexis, did that answer your question, or do you still have a question about that? So in this second one, you're going to integrate it over the integration bounds here are 8 to 12. And so those are evaluated at 12, and then you subtract off the 8. Yes.
So if we were to go for the entire time interval for the 32 seconds, would we still end up getting?
So the way the average works though is only over one time period. So you wouldn't want to go over 2 time periods. It will still be skewed if you do it over the 2. So just one time period. Does that make sense?
So you try to focus on one.
Uh-huh.
Not two.
Correct. Yeah, because the periodicity repeats, just focus on one time period. The nice thing is if you have a sinusoid here, it goes to 0. So your average is going to be 0 if you have a sinusoid. Unless it shifted DC shift up or down. Then you would have an average from that one. All right, any other questions on finding the average of a signal? Okay, so the other thing we want to find is that RMS value. So the RMS, sorry, this is annoying without a Apple Pencil. I missed my pencil. Okay. So now for this one, we are going to take the RMS. So this will be IRMS. All right, so we have now 1 over, well, the square root of 1 over 16. And then we're going to integrate each one of these. So you're going to do again, the 0 to 4. And then this will be minus 12 squared dt plus 4 to 8. 3t, what is it again? 3t minus 24 squared dt. And then 8 to, I think it's 12, yep, 12. 3t minus 36 squared dt. And then plus 12 to 16 minus 12 squared dt. And then this ends up giving us 9.8 amps. All right, questions on this?
So
Yes.
The purpose of this is to get an AC equivalent to current.
Yeah, to current or voltage. So we could do the same thing with a voltage graph and get the VRMS. And then we could use that to find, well, in complex, there's a little bit difference. We could find the average power, which is going to be in the DC kind of equivalent, but then there's a complex portion of it. And so we'll talk about that in a minute. But yes, we can use these values to actually find that complex portion of it. But these do effectively give us what the DC value would be if we were to measure these. So when you measure on an oscilloscope, you'll see the full waveform like this. But if you use your digital multimeter, you're going to measure an RMS value. So hopefully now you kind of understand what that RMS value and where it comes from. So you guys ready to do one on your own? I gave you an easier one than that one, but this is the one. So for this graph, determine the average and the RMS values. And for you guys online, if you want to just from 4 to 8. If you guys just want to stay in this main room, you are not on speaker, so you guys can still talk. So Alexis, to answer your question, so when you have an integration, you take the top one and then you plug that into the function and then you subtract off the bottom term. So you integrate it from 4 to 8, and then 8 would be the first one, and you subtract off the second one, which would be 4. I don't know if that clarifies. Where's that one back again? Oh, I'm stupid. That's why.
Why don't you do show us Sorry, That's G from 0 to yeah. Maybe it's actually wrong. That's not this is the formula outside. You're wrong. It's 3 times 1 now. So that's 1. So 2 times 2 times 2. 2 times 1 now is 1. Divided by 2. So that's 3 divided by 4. No, that's not 8. 2. Oh, it's 3 times 2 divided by. Yes, 3 times 2 divided by 2. So 3 divided by 2. See the hard why is my I have nothing to do with it. The rise is the rise to yeah. I just know you taking any high school classes? Yeah.
Yeah, that's.
So you're in high school, you don't get any high school, you've been over. Well, I know that my arm is you literally don't, you can go to the high school. I think I got well. Yeah. That's why it's Oh, I didn't square the whole equation, or did you just square X? That's not what I'm missing.
All right, so here is the solution. So you write this, you have to first, what is the equation for that line? And so mx plus b again, m in this case is the rise over run, which is 3/2. And then it intersects at 0. So it's 1.5t plus 0. And so between 0 and 2, you have 1.5t. And then it just is 0 between 2 and 4. And then it repeats the same one. So we're going to only evaluate it over one period, which would be from 0 to 4. So 1/4 for the average. And then evaluate it from 0 to 2 at 1.5t. That gives you 1.5t squared over 2, and evaluate it from 2 to 0. What? So it's 1/t. So the average equation is 1/t, and t is the time period. So that is how long before it repeats again. So you look at that period, and in this case, it goes up to 4, and then that portion repeats itself again. So this would be t.
Oh, wait, no.
Okay, so it's just whatever, however long that time period. So this can be skewed, when you look at these, you're going to look at this on an oscilloscope. You're not going to have an exact 0 time frame. So when you look at this on an oscilloscope, you have to look at that and say, okay, where is my period here? And you define where 0 is, and then you look at where it will repeat itself. So in all of these nice graphs, you get 0 told to you, but in an oscilloscope, you're going to have to define where that 0 point is. Okay. So if that is the equation that's describing this, then you can do the average is 1/t, and then integrate it between each portion of it. You add up each portion that's different in there. And so the first portion goes from 0 to 2. 1.5t, and then integrating that, it's 1.5t squared over 2. And then the integration bounds goes from 0 to 2. So this portion is 1/4, 1.5. You plug in the first top one, and then you plug in the bottom one. So that will be 1.5 T 2 squared over 2 minus 0. And that gives you 0.75 volts. For the RMS portion, again, you have to know the equation. So on this equation for the average, it's going to be the square root of 1/4 and then integrate 0 to 2 and then the 1.5 T squared. And so integrating that becomes T to the cubed over 3 and then 1.5 squared is 2.25. All right, questions on this? Did you guys get this? I'm seeing some yeses, some nos. Some majority yes. Okay. All right. All right, so this is kind of the first step, is understanding these terms, understanding what they mean equation wise. Yes.
So what exactly does it mean to take the root mean square and what, how does that compare to taking an average?
So you can see here the differences, like the average is literally in the middle. So that would be 0.5 or 0.75. That's usually the middle of your the middle of the average. So if you have a sinusoid, you know, it's easy to see that average is right in the middle at 0. So when you have something like this, where over that time period, well, you have portion of it, a triangle, it's hard to see where that average is. So that's why you use the mathematical equation to figure out what that average is. RMS is going to be what, sorry, what makes it equivalent in power to if I have this input coming in and goes through a circuit and then gives me the output power. So it's usually a little higher than that average value.
It's the equivalent of power, the other one's the equivalent of whatever, like,
Whatever the graph is, yes. Yeah. So when we're talking about RMS, it's typically kind of related to power. But you can write something like the voltage RMS of the voltage or the RMS of the current or the RMS of the power, but you use that value to say, because it's an AC signal, if I was to use these values, it's going to give me the equivalent power I would see if I was using just DC voltages. That makes sense? Sort of. Yes.
So in practical applications, like we've got a device in our home that runs off, 120 AC or DC voltage. Like we could, so to say, effectively, obviously we need a time period for, well, let's just say it's not a perfect sine wave.
Mhm.
We could effectively use the RMS to say, well, how much watts of power does this blender use over the course of a minute? Well, that would be watts per second, but how much power does it need to run, I guess, to say, is that kind of like where the stuff gets used?
Yeah.
In practical, this is just a theoretical exercise.
Correct, yes, and that's what we're getting to, is we want to use this to say, well, as a designer, how do I use this information to actually match up the circuit so I can provide the maximum power to whatever the load is, a blender in that case. So I want to kind of know what components, so I'm going to fight all the parasitics that are coming out because I plugged that in. That cord of the plug itself has a parasitic resistance and capacitance to it, and even a little bit of an inductance to it. And so because there's physical things there, that's going to create it to give you some noise, and then you want to offset that. And so this is why we're looking at that. The other thing about, like, if you look at the average of the power coming out of a wall, that is a sinusoid. So your average is going to be 0.
Yeah.
So if you look at the power average there, well, you're like, well, it's not 0. And so that's why we're looking at this for AC. it's really not zero. It really has some value to it. And that's where the RMS comes into play, because it's an AC signal that I can now represent and actually get a value for what power is actually going to be consumed.
Yeah,
Does that help?
it does. So essentially, like if we did the RMS for a perfect sinusoidal wave, it doesn't give us zero.
Right, the RMS value won't.
Even though our average would be zero, if we did the RMS calculation, we wouldn't get zero.
Yeah.
Okay. Good enough.
Okay, other questions? Okay. All right, so now we're moving on to the next concept that we need to understand. So that next concept is complex power, average power, and reactive power when we have an actual circuit. So there's some, again, some terminology that we want to look at. So power, you know, we think of it, well, if it's in terms of, oh my goodness. You know, power is equal to voltage times current. And so if we have these voltage described here as 4 cosine 377t and I of t equal to 3 cosine 377t, then what, you know, does this result in? So when we multiply these and take all the properties of the actual, like, if you remember the cosine squared properties, let's see, what was it that you use? Yeah, so it's because you're multiplying cosine times cosine, you use the property of the cosine, x times cosine y gives you 1/2 cosine x minus y plus 1/2 cosine x plus y. So when you multiply these together and you have two cosines, you get this cosine xy. You're going to end up with the equation of power that looks like this. So it's going to be the amplitudes 4 times 3 over 1/2, and then cosine of the 30 degrees minus the minus 30 degrees plus this 4 times 3 over 2. So when I graph this, this is kind of what I look at. So current is the black one, voltage is the blue one, and then you can see that the power has a frequency change versus the cosine and versus the voltage and the current. So voltage and current keeps the same frequency, but they're just shifted off of each other. You also, terminology wise, can say that the current, sorry. Objective, oh wait, where did it go? Okay, the current is shifted 60 degrees behind that of V of t. So you can look at that by the equation. You have 30, and then the I of t is minus 30. So when you look at that, it's considered shifted. 30 to minus 30 would be a minus 60. And then that frequency of power is much faster. It's twice the frequency time frames. Okay, so this is kind of what you're always going to see, is that that power has almost twice the frequency of your current and your voltage. All right, so average power, we're going to do the same thing we just did, 1 over t, integrate it, and now you're going to integrate that function. And in terms of VM is the peak This is the voltage amplitude. So in our previous graphs, that was, I think, 4. Is that 4? Yeah, that one was 4, and this one is your current amplitude. And then this is the phase shifts of your voltage minus the current. And this term is called this term together is called the power factor angle. And that's, again, another term you need to understand, power factor angle. And so that is the shifts of the voltage minus the shifts of the current. And that is going to help us determine some information about the average power. So this would be the equation for the average power. And when you integrate, again, a cosine, the average of this is going to be 0, right? So that means that this term goes to 0. And so we're left with this equation for the average of Vm times Im over 2 cosine of that power factor angle. And that's going to be in watts. Okay, any questions about, like, this will be another equation that you need to know.
Why is it voltage minus current and not like current minus voltage?
That's a good question. It's because the current is usually behind the voltage because you're supplying the voltage typically. That's not a really good answer. Let me think about it.
Kind of that like voltage leads current.
Mhm.
Can't remember that old saying. but-
No, that doesn't
Yeah.
help. But yeah, it's because the voltage will always be usually leading that current.
So, and that's just like due to typical application or actual like kind of physical. principles?
It's the physical principles of it,
Okay.
but I have to think about a way to describe it better.
Sounds good.
So, all right, we're gonna take a step back to review a little bit with chapter 7. So with chapter 7, it goes back into all the phasors that you guys did in 1240. So complex numbers were part of that. So some of the common properties, I've given you kind of this table, which is a great useful table to remember a lot of these properties. And then also how to convert between polar and rectangular to go back and forth. So if you have a rectangular form, you can write it also in the polar form. And so if you have the polar and you want to get back to the X one, it would take the magnitude of Z cosine theta. If you wanted to find the imaginary part to go backwards, it would be Z, the magnitude of Z sine theta to get Y. Yes.
So I always get really confused about this part right here because I get confused specifically on like the difference between the Laplace transforms, like when we're in the Laplace domain or in the basic domain. Like what's the distinct difference between those two?
They're exactly the same if you put S is equal to J omega. So with the phaser, you are only finding it at one frequency. That's probably. So you're only finding it at one specific frequency value. When you do the Laplace, you are doing it in the S domain, which could be across any frequencies. So the Laplace gives you more information, but there's some insight we get from this phaser domain, and that's why we're kind of going back to it to be able to understand a little bit more about the characteristics of circuits. Does that help clarify what the differentiation between phaser and Laplace?
So plus does a variety of frequencies and phasers specific to one.
One frequency, correct.
Okay.
So in order to find the phaser, you find it at like L is equal to SL, where S is J omega, and that omega needs to be known. And so it's one value at that specific frequency. Yeah. So, okay. All right. Theta depends on where your vector is in this quadrants. So I'm going to draw each of these in different quadrants. All right, so if your X, which is your real component, is positive, you're going to be in this first quadrant. Oh, wrong one. So you can just take the inverse tangent to find that theta as imaginary, which is Y, over X, which is the real. If your X is negative, then that means that you're in the green quadrant there. And you need to add or subtract 90 degrees from that value. And then if, oh wait, pi 180. All right. If X is 0 or less than 0, that means you're in either the green or the blue. Say that. And you can do plus or minus 180 because you can either go this direction or the other direction.
I didn't know when to do plus or minus 180.
With
Sometimes we don't know plus or minus 180, but when do you do that?
so say you have a negative real and a negative imaginary. If you plug that into the inverse tangent, that's going to give you a positive value out. And then you know that you're not in this quadrant. So that's why you have to add 180 to it. Does that make
I
sense?
think so, yeah.
So essentially, it's just understanding that your imaginary number, like the real part is the X coordinate, the imaginary part is the Y coordinate. So you kind of just need to understand, based on those coordinates, what quadrant am I in, knowing that tangent of -1 really will only give a value between what, like 0 and 5. It won't give you the values for the third and fourth quadrants. You need to know, like, kind of do some logic.
Yeah, so that's why I'm going over this, is you do need to understand, like if you have one, like if you have a positive real and a negative imaginary, that's going to give you the right angle. That will give you this angle here. And it will be a negative number. So it will be like -40, which you're like, okay, that is in the right quadrant.
So it gives you from pi over, or like between pi over 2 and -pi over 2. It gives you the values of quadrant 1 and 4.
Yeah, it gives you the right ones. So these are going to give you the right values. But if you have a negative real and a positive imaginary, it's still going to give you this angle here, which is not the correct quadrant. So that's why you have to add 180 to it. And then that will give you the right quadrant, which is over here in the third quadrant. So you do have to kind of understand, where is this vector? All right. Other properties that are really useful, you know, J is going to be just angle 90 degrees. It's one up. And a negative J will be minus 90 degrees angle. And so that is when your vector is just straight up or, straight down. All right, so complex number review and a review of how to do the phasor domain, which is very similar to the Laplace. You plug in that, though, instead you do a specific value of omega in there to get a specific value for the inductor and capacitance. So that's the difference, is it has one specific one. You also have to have your source in terms of cosines to be able to change it to that phasor value. And the phasor, remember, is the amplitude becomes the magnitude and the shift becomes here. So why is this minus 135 degrees? And the shift at sine was minus 45.
Isn't the shift from sine to cosine minus 90 degrees?
Yep. So you have to change it first to cosine, and then from there you can take the phasor for it. So then you just do the same steps as before. You do node voltage, KVL, KCL, Ohm's law. You get your set of equations, and then from there, your end result ends up being a phasor in the polar. So you write it in the polar coordinates, and then from there you can translate back into the time domain, which in the phasor, this would be 6e to the minus 105j. And so that then translates, let's write 6. Oh, I wrote magnitude of 6. 6e to the minus 105 degrees. And then that translates back into the time domain as 6 cosine omega t, which is again that same omega frequency that we started with. So this method again is limited more than the Laplace transform because we can only do it at one frequency. The input needs to be a sinusoid only, where in the Laplace, you could have a complicated input to be more than just a sinusoid. So why we're doing this is to make some understanding of characteristics of what's happening in the circuits themselves. So this is called a phasor diagram. So if I was to graph my VR, it would be a real value. So this is where the voltage input is only a real component. And I put that through a resistor, I get only a real value out. If I have a capacitor though, my current now becomes J omega CVC. And remember, J is going to just be a vector at 90 degrees. So that's because J is, 90 degrees. And an inductor is a minus J of VL over omega L. And so, well, okay, let me back up. So this is J omega L. And then when you take the current is V over L. And then you can bring the minus J up to the top. So that's where that minus J VL over omega L comes from. So what this means is that either if you're in a resistor, you get real and a real input, you get a real output for current. If you put in a real voltage for a capacitor, it shifts at plus 90 degrees. And then for a inductor, it shifts at a minus 90 degrees. So with these, they're either plus or minus 90 degrees. We're going to use that concept in just a second. So now we can go back to the complex power. with that understanding. And with the complex power, if we look at writing them in the polar coordinates of that VM, which is our magnitude of, remember our V of t was VM cosine 377t minus some shift or plus some shift. So that shift of V, and then the I had the shift of I, so theta I. We're going to introduce now this new term S called the complex power. And the complex power is our P average, which is the DC component of this. So we're going to again use everything in RMS for that average power. And then we have now a new value that's the imaginary portion called Q. So P average is just the real portion of this complex power. It's the average absorbed power. And now this new term Q, then this average power is in watts. Complex power, because it's complex, we now have a new unit to it. It is watts, but because we want to differentiate that it's not DC, we use this one. It's called volt ampere now. And you do VA. Even though that's watts, it's just to distinguish it that it's complex. So it's called volt ampere. And we have now this peak exchange power, which is the complex portion of it, is going to be the imaginary part of this complex power. And its units are called VAR. Again, it is watts, but to differentiate and distinguish it, we now have this new term, volt ampere reactive. That is just to differentiate it that it's in the imaginary side of this, okay? So some new terminology. So next time we're gonna go over apparent power, power factor, and then we're going to start looking at actually solving some circuits to find these values. All right, any questions? Yep, so this is all chapter 8 so far. And then once we're through the complex power, then that will be well, yeah, chapter 8 with a little review in chapter 7. All right, see you guys.